All right, so we're recording. So that shows just then what we've got planned for this week and why those two are so important. So typical week, here's our overview discussion board. There's a couple of refresher readings on vectors and structs. Definitely check those out. Now here is some sample code that I posted, and this is what we'll be looking at today. Some of the many vector methods that we can employ. So you'll have that at your disposal. And then we finally have two assignments this week, both 50 points. One is to create a struct on polling places, and then the other is to have a vector of structs. I also have a previous video on structs that I had from a previous semester, and I've posted that. You can review that, and then of course these videos, I'll post all of those. All right, so does that make sense? And any questions on kind of where we're going this week or the next couple of weeks? All good? Okay. All right, then let's jump in, and we'll take a look at. Do you know what I wanted to do first? Actually, before we look at vectors, I wanted to kind of give a broad overview into these data structures, and I made a list here. And what I'd like to do is just sort of give an overview of what the heck are we talking about? What are these data structures, and what do they look like, and which ones will we be covering in the course? So I wanted to go over that just super quickly and kind of maybe draw some diagrams and show, okay, this is this and this is this, and kind of give a little more of an overview on the entire course. So now let's see. Ricardo has a great question. If you haven't taken 200, will those videos from previous classes be provided? And yes, I'll post every video that I have from previous classes, as it pertains, of course, to our course content. I won't give you I won't post a video on something like functions because we're well past that. However, on classes, especially as we start to convert from structs to classes, and then as our classes get more complex with split implementation files and inheritance, then yeah, I'll have plenty of those. Okay, plenty of those. All right, let's do. I'm going to go over to the iPad now, and let's take a good hard look at what are we talking about. So. All right, so here we go. And let me pull up the chat again. And then Ricardo, your question, will we learn heap sort? Yep, we will. We sure will. And I'll get into that as one of the ones that we'll look at. Okay, so I'm going to just start drawing. I think that'd be kind of a fun thing to look at. So the very first thing that data structure that we're going to tackle here, and I'm going to have you tackle it actually as we start to build our foundation and review on classes. We're going to start with this one because it's one that's probably easiest to implement without a class. So many of our data structures will actually be implemented as abstract data types, and that means classes. So if we're going to create a binary tree, for example, well, we would use a binary tree class and just simply create a binary tree object. And then we're going to manipulate that object. Linked lists, though, we can pretty smoothly do those without classes. So that's going to be the very first thing that we'll tackle. Now, what is a linked list? Well, a linked list is precisely what the name implies. It is a list where one element is connected to the other. Nice and simple. And what we like about linked lists are that they sort of kind of substitute for an array when we want to start thinking about a dynamically sized array. In other words, an array that we can, at runtime, we can insert an element in, and the element's just kind of spread out, and our inserted element is there. Or same thing, if we take one away, then they all just sort of go back in place like that. And we can't do that with arrays, because arrays must be, the size of arrays must be declared at compile time and cannot be changed. You can sort of mimic the behavior to make it kind of look like it changes, but it doesn't really. So a linked list is what's going to be one of our preferred data structures of choice whenever we're talking about a dynamic array. Now, what a linked list is now these use pointers, and don't worry if it's been a while since you've had pointers. Don't worry, we'll have a good pointers review before we really start getting into these. But we can just basically have a pointer that's going to point to an element here. And this element would have an integer here, and then it would have another pointer here. So we can see that this might actually end up being a struct. So it's a struct with two data elements in it. One would be an integer that's actually holding the data, and then another one would be a pointer to a pointer to an integer. And a linked list is great because if we need to add something, well, it's a very simple matter of we can add another node here. So now there's the data point in it, I. And rather than having this node here, pointing to null, and whenever you have an arrow, a pointer arrow pointing straight down, it's assumed that that's pointing to null. Instead, we just change that to now the pointer is going to be pointing to the new node. And it's this new node's next pointer that now points to ground. And you can see then, well, all right, well, we can kind of extrapolate this idea here where let's say we had a new node created here and we want to insert them between these two. Well, that just becomes a matter of managing our pointers. This pointer here that we just created would now point to that node. And the pointer that we had previously created, we change its destination, and now it's going to point to the new node. So you see that we've just inserted a value inside this linked list. And now we've got elements 1 and 2 and 3, and 3 points to ground. It points to the null, and that's pretty much it. That is a linked list. Some of the operations that we can do, of course, we can traverse a linked list to process it. We can process the data, insert one, delete a node. We could delete the last node, delete the first node, insert the first node, insert last. All of these type of operations are going to be important for linked lists. And you can see here, since we're talking about, well, what operations would apply to a linked list? Well, now it might start to make sense why we would implement a data structure as a class, because that class is going to have all of the definitions for these types of operations that we can do on this data structure. So we would have methods for insert, delete, insert beginning, delete end, many types of methods that would work on this class. So this is a singly linked list, and it's called single because there's only one pointer in each element, and that pointer is pointing forward. I should go this way. It's pointing forward and pointing at the next element. So this one goes to that one. This one goes to that one. Now, so that's a single linked list. Here's what a double linked list is, and as you guessed it, it's going to just look a lot and feel a lot like we just did. We'll have a pointer pointing to the first element. And I'll just do I'll do 3 nodes for now. All right, and there's that third one that's pointing to ground or pointing to it's the null pointer. Now, a doubly linked list is, you guessed it, rather than having pointers that are only pointing forward in the chain, we also have pointers that point back in the chain. So they're pointing to the previous node, in addition to having the next node being pointed to by a pointer. So in this very first one, of course, the first node doesn't point to anything, so that will point to ground or to null. Here in this middle element, that middle one is simply going to point to the first element. And then same thing here. This one is also then going to point to the immediately preceding element. And why would we do this? Well, a doubly linked list like this is going to be a little bit easier to manipulate, especially if you have the situation where you're going to delete a node or insert a node in the middle. If you have a singly linked list, and we'll get to this when the time comes, when we get to a singly linked list, we'll need to have some extra pointers assigned to keep track of, well, where are we inserting? But with a doubly linked list, you need fewer of those extra pointers to keep track of where the pointers are pointing. And that's because we've got the doubly linked list. We've got both the forward and the backward. So that'll be a doubly linked list. Same thing, we'll implement it in a class. And kind of the same operations as before, you know, insert, delete, insert front, delete front, and all of those. All right, so those are our linked lists. All right, questions on linked lists? All right, then the next thing we'll take a look at, this is the stack. And stacks are really one of the easiest things to implement. And you'll probably agree because it looks and feels a lot like a vector. Now a stack is precisely that. Just imagine a stack of dishes. Stack of dishes. We will have this stack of dishes with our data elements in it, and the operations that we'll be able to do for this are going to be to put an element on top of the stack. And we could also then pop an element off of this stack. And that's pretty much it. A stack is very, very simple to implement. And it's going to be one of, after linked lists, it'll be one of the first things that we start to take a good look at. Now, it's not designed to take anything out of the end, just because that's the feature of this data structure. If you needed a data structure where you might have to insert in the middle and delete in the middle, you would have to choose something else. You could choose a vector or a linked list. But a stack is simply going to be this idea of LIFO, last in, first out. So the very last element here that was put into the stack, and we can call it pushed into, this last element here is then going to be the first one to be popped off. If we wanted to go down here and get this element, this red element here, well, we would have to pop off the first two elements of the stack. So we get this one removed and this one removed. And then now the element that we're looking for is going to be at the top of the stack, and it can now be processed. So LIFO, last in, first out on a stack, okay? So that's a stack in a nutshell. Here is the next thing we'll look at in a nutshell, which is a queue data type. And this one is the easiest, or is going to be easiest to remember. Just thinking about a line to get into any venue. A line is a queue. And so if you have a queue here of people waiting to get into that restaurant or into the movie or into the bar, but of course not yet in Alameda County. This is going to be a first in, first out kind of a data structure, a FIFO, first in, first out. So this is the front of the queue, and this is the end of the queue. And just like people getting in line, you're waiting to get checked out at Safeway, and finally it's your turn. Well, now in front of the line to process this queue, we're just simply going to pop off an element at the front part of the queue, And we have then the remainder of the queue to store in our data structure, and then we can go ahead and process the front. New entrants to the queue get added to the end here. So the end will grow as our operations are conducted, and the front part of it will gradually get lopped off as we process the front of the queue. So same kind of a thing with what expected operations we might have with a queue. Certainly a push, we could push a data element into the end. A pop, we pop the data element off the front end. Here also, you wouldn't use insert, you wouldn't use delete, other than the front. And that's because, this is not the data structure for that. You would use something else. All right, so that's a queue, a Q-U-E-U-E. It's kind of a weird spelling, but queues are pretty common in computer science. All right, we'll also look at binary trees. And that's where you would have a data element, and sort of like with the doubly linked list, this data structure is going to have 2 pointers to it. One points to what we'll call a left subtree, and the right would point to what we can call a right subtree. And those then are just going to be identical little nodes, using the same struct, and they'll have those pointers then. And I'll point this one to null first, like that. And a binary tree is going to do a number of things for us. First of all, a very large data set organized into a binary tree structure is going to be so much faster to search and to find that result. That's why we primarily like binary trees. It's also going to be able to give us the ability to just create a very large data structure very rapidly in a very organized fashion. Because if we decide to go down this tree to do some work and create some extra nodes, we can do that. We go down this one, extra nodes. So at the end of the day, a binary tree, will, and I'll just put kind of big dots here for the nodes that you can imagine, but you can see here how a binary tree would ultimately result in X number of subtrees, and we can have leaf nodes. These bottom ones are like the leaves of the branches. If you kind of put this binary tree the other way with the root down and going up, you see that those branches are kind of pointing up to the sky. So that's going to be a binary tree for us. And then same thing there, we'll have operations like if we're going to delete a certain node here, well, we've got some pointer management then to take care of, don't we? We've got to reroute those pointers, so when this node is removed, the pointers are still pointing to the correct nodes, and the binary tree structure remains in place. Okay, so that's a binary tree. Let's get to a B tree. And what a B tree is, it's a balanced, self-balancing tree. People sometimes get those confused, B for binary. So they think B tree is a binary tree. Well, it is, but it's a lot more. It's sort of a binary tree on steroids, and that's why we call it a self-balancing binary tree. And what this does is, if we create a node here, what this does is a self-balancing binary tree will have a number of data elements in each node. So it could have, up to, X number of actual data elements in the node. And then not only that, it can have, up to X minus 1 pointers toward child trees. So then this one would point over here to another node like that. This one might point over here to this one, and this one might point over here to this one. So you get the idea there. Now, the idea of a balanced tree is that it doesn't get very deep at all. Matter of fact, it'll only get, if we're looking at it in terms of layers, it'll be 3. And layers in binary tree lingo is its depth. So the depth is going to be no more than 3. It's self-balancing because as we go in and try and insert a node here, let's say we wanted to do a node there, and if that's full, well, what happens is this node actually gets extracted, and then we get new nodes created from the remaining data elements. So these then all become new nodes. This one points to a new one now, and now we've got a different structure that's going to look kind of like this: 1, 2, 3, 4, 5, 6. So trying to insert a node in this element right here, where I'm drawing in blue, was unsuccessful because the node was already full. So it just split off and created new nodes in order to give that extra room. And this is what we mean by a self-balancing binary tree, because it'll do these types of operations and remain balanced. So that's a B tree for us. We'll have fun with B trees, that's for sure. Let's look at hashing. Hashing is searching, and what's interesting about searching is the complexity. If you've got a 1 million element array and you've got to search for a certain value, while searching, of course, like we saw like we saw before, searching can be very, very slow if you're just doing a linear search and looking one thing at a time. And it could be on the order of n, the number of examinations that you have to make. Well, a hash is going to really compress all of that for us. What a hash does is it creates a hash table. And what a hash table is let's say that we've got an integer array here. It's just giant, 1 trillion elements, let's just say. So here they are. Here's all 1 trillion, okay? If these are the data elements, I'm going to say just and so on. Rather than storing those, or in addition to storing those, we would create what's called a hash table. And you get a hash table by putting these data elements through a function. So these all go through some kind of a hash function, h sub x. And what you do then is store the results in a different kind of data structure or pool of results. And what this does then is it lets us zero in right away on where the data is. So here's a good example. Let's say our hash function is simply, we're going to take the integer and mod it by 10. That's our hash function. Well, what this means is, since the mod operation only gives us values between 0 and 9, well, what this means now is we have got a 9-element hash table. And here's 0, 1, 2, and here's 9. And these are all of the possibilities of that hash function, h of x. So 65, our very first element, divided or modded by 10, is a 5. So here in the 5 bin, let's just suppose that here's the 5 bin right here. We would put, let's say this is the 5 bin. My math or my graphics art skills today are lacking. All right, here's the 5 bin, and we put in the value 65 here. Just like the 324 bin, okay, that one's going to go into the 4 bin. So 324 goes over here, 324. 971 goes way over here, 971. And you can see that we kind of put the values in these in these tables. Well, then when it comes time to search for a value, the first thing you do is you look at the hash function. So let's say that the value we're looking for is 329. Well, first we check out, well, what is 329 modded by 10? And it's 9. So we don't search this array at all for the value. Instead, we go to the hash table and we search element 9, and we're going to look for 325 in that bin. And the number of elements in that bin are going to be significantly smaller than the number of elements in the original array. So that would make our search even more efficient. So that's sort of, that's basically what a hash is going to do for us. We'll look at the various hash functions. Some are more efficient than others. So you get the idea there. All right, so does that make sense? Those are the data structures that we're going to examine in this course, and just kind of a quick graphical representation of what those are. So does that make sense, everybody? All right, good. I got a thumbs up from Ricardo. Thank you. Benji, good. Saya, all right, good. Oliver, all good, all good. All right, well, let's take a look now at our vectors now. Do a real quick vector review. I'm going to go. I think we'll go straight to Eclipse here because I don't think I need to draw this out. This is just a real quick. Come on. Just a real quick refresher and a primer. So here's that code that I put in Canvas for you all. I'm going to zoom it in a little bit. All right, there we go. How is this zoom level, everyone? Can you see that okay?
Looks good to me.
Okay, good, good, good. Benji, you've got a great question. I do recommend Eclipse, but you're used to Visual Studio. Is it okay to turn it in using that? Yeah, absolutely. Yeah, you have your choice of IDE in the class. I do recommend Eclipse because it is an industry leader, and it's pretty darn robust. Visual Studio is good. Microsoft tends to point that to just creating Windows applications, which kind of is not how the world runs. But it does a pretty good job. We won't be looking at any of the MFC stuff here in our class because that's almost exclusive to Windows and VS, and that's all the Microsoft Foundation classes. Ricardo, is it better than code blocks? Yep, it absolutely is. Code blocks is just a commodity, kind of a beginner IDE to get you out of COMSC-210. But if you're going to become a coder, if you're going to become a developer, then you'll want to go to Eclipse because code blocks, first of all, it doesn't neatly handle file operations. You've got to go through some real machinations and ordeals just to simply get a file to work. So that's my theory on code blocks. I did use those for one semester at DVC, and honestly, I hated it. Okay, let's get back into our vectors. So here, declaring our vectors. Actually, you know what? I think I'm going to go. No, I think we can just do it this way. So this code here for declaring those vectors, we've got a number of ways to actually declare, and then alternately, or I should say optionally, you can initialize your vectors. You can initialize them to an initial size, and you can initialize them to initial values. So here in line 8, there's our first one, and this one is just simply creating a blank vector. Here in line 9, you can create a vector that's based on a previous vector, or in other words, it'll copy it. So myvec, we throw that in as an argument, and now myvec2 gets created just from myvec. So it makes a copy. All right, here's the third one. What this is going to do is it's going to create 10 blank elements, sort of a starter pack. You get 10 free starter elements into this vector. And of course, they're uninitialized, so you can't use them. You'd have to definitely use them only after you put some values in them. Now, some people ask, well, why would I want to create a 10 element vector at declaration time when I could just create a blank one and push values into it as I see fit. And yeah, that's probably the most common approach. I usually just create blank vectors and then I push values in as the program sees fit. But there may be some use cases here and there where you'd want to create something large. Create something with the size known ahead of time. And here's a good example. Let's say you needed a vector filled with the integer 200. Well, this is going to do that. This myvec4 is going to create a 10-element vector and initialize all of those values to 200. Okay, so you can see here when I ran this, here is the results of that vector 4, myvec4, and it's got the 10 elements all initialized to 200. Let's see, Ricardo, it allows you to not have to create and destroy objects in the process of making a vector of 200 elements. Yep, absolutely. If you know you've got the requirement for a vector of a certain size, well, yeah, just go ahead and declare it. You can always delete things and add things later, but you can kind of save some processing time if you know that your vector is going to be of I should say of approximately a known size. All right, here's just a typical range-based for loop to process this vector. And the range-based for loop part is this part right here. And that's just saying, all right, as long as there's an integer that I can extract from the vector myvec4, go ahead and extract it and assign it to the variable val. And then here within that for loop, is just a simple count that's going to count val and a space. So super quick range-based for loop for the vector there. And I'll use these range-based for loops for all of these. All right, here's some code on how to clear a vector. Note that this doesn't delete the vector. It just simply clears it. And what does clearing mean? It deletes all of the elements. So at the end of this ordeal, you would have just myvec4 is strictly blank. It's you've got a pointer pointing to the fact that there's a vector there, and that's it. No data exists in it. All right, there just to kind of refresh also about swapping vectors. You can, with one instruction, take two vectors and just swap them. And we would do the myvec3.swap method, and what's interesting about that is it doesn't matter which order that you do these in. You could easily do a myvec2.swap and swap that with myvec3, and either of those are valid. You just have to pick one. All right, so they're swapping two vectors, pretty straightforward. Pushing elements into a vector, this is where the real power of the vector starts to come in. Because if you run out of space, you just simply push another value into it. So we use, in C++, we use our pushback method. And there it is. So what this is doing is it's going to push in 0 through 4 into this vector. And then I've got a quick range-based for loop there just to validate that we've in fact pushed 0 through 4 inclusive into the vector. So when we ran that code here, this was our output here, pushing elements into the vector, into a vector, and then we get the 0 through 4, just like we had planned. So pretty straightforward here. Now we can push elements into a vector. It goes into the last slot, I'll say, the last element. So this sort of acts like a stack more than any other data structure. If we pop elements, well, we pop them off of the end. And the end, just like a stack, a stack of dishes, if we were to rotate that this way, we're always then pushing into the end and popping off of the end. So the beginning stays the same, and our push and our pop is going to just deal with the end. So you'll have to keep that behavior in mind when deciding which data structure you want. So popping elements off that end, we just use the the pop back method here. And the pop back method, of course, doesn't take any arguments because we're just going to delete that last element. So you can see here in this little code block that I've got highlighted, I've called the pop back method twice. So we would expect to see two elements off the end of this vector get deleted. And sure enough, we do. When we ran that, we got these results here. And we see that the elements that contain 3 and 4 are gone now, just simply deleted. All right, so that's our pop back. And just remember, it always pops back at the end of the vector. Okay, last in, first out, that type of a concept. All right, now the next kind of code block, the next couple of code blocks that I have, they talk specifically about how to delete a specific element other than an element that's not, in the back. To delete the last one, we just use pop back. But how do we delete an element that's in the middle somewhere? So here's the code that would do that. So first of all, what we're trying to do in this example is we're going to try and delete the element that's in location 1. And that's actually the data element also, that's just 1. So to get to that, what we do is we use the erase method, myvec.erase. And the way vectors function is that we wouldn't want to have a hard reference in here because vectors are so dynamic by design. It would be very hard to maintain a pointer to the first element all the time, especially if it's so dynamic. So what we do is we have to, first of all, give a reference point. We've got to supply a navigational beacon so that the compiler will know exactly what we're talking about when we want to delete this element. And what we do is we call the .begin method. And what that does is it actually returns a pointer to the first element in the vector. And what we can do there is then start counting from that vec.begin place. We just can start counting and provide an offset, 1, 2, 3, 4. And if it's that one that we wanted to actually delete, well, that's the offset that we give it. Now, fortunately, the way that we count these vector elements is the same as with array elements. So we start with index number 0. The first element is index 0. Same thing in a vector. So we kind of, it's very convenient here that since we wanted to delete location 1, and that means index 1, well, this myvec.begin, we just add 1 to it, and that's going to get us from 0, and now we add 1, and it's going to get us now to 1. So unsurprisingly, the offset that we have to enter in that erase instruction is going to be the exact same integer literal that we need at the location. So if we needed to erase the 4th one, then we would just do a +4. I'm sorry, not the 4th one, I should say. If we wanted to delete the index 4 element, then our offset would be +4. All right, so that's how we would do that. And then you can see then when we ran it here, that in fact, we did get that middle element, the number 1 element that was deleted when we ran this. So that did successfully find the right element and then sort of surgically extract it and delete it, okay? All right, so that is inserting for us. Deleting for us. Let's talk about inserting elements now too. Now we kind of have the same offset requirement for inserting. First of all, we would use the myvec.insert method, insert, and it takes 2 arguments this time. First is, where is the element to be inserted? And then second, what is the data item that we have to insert? So this line 47 is going to be both of those. First, the vec.begin +3 says we're going to insert this data element so that the new location is at index 3, 0, 1, 2, 3. It's going to be right there. so that vec begin offset is going to be just +3. So that's where our vec begin, oops, that's where this highlighted offset comes into play now. There we go. And then finally, I'm going to insert the value 3000 just to make sure it stands out in this insertion operation. And then here we go, when we ran this, you can see now that we've got all of those 200s, but look at that, right in the middle at location 3, 0, 1, 2, 3, we've got element 3000 now, 3000. All right, and then finally, just the last thing to take a look at, if we wanted to delete not just one element, but a range of elements, well, we just give it a couple more pieces of data, and it's going to know what to do with that. So first of all, to delete a range, the format of it is this way. We use a square bracket with a 3, a comma, then a 5, but then we sort of mismatch the bracket. We don't have a bracket closing, we've got parentheses closing. And what this signifies is that this specifies the range 3 to 5, but it's non-inclusive. So this is only going to give us 3 and 4, and it does not include 5. And this is a very common C++ nomenclature to describe a range. And it's more, I tell you, more often than not, that first element will always be included, but the last element you specify will not be included. So deleting this range of elements is no different from that schema that I just mentioned. So here, the first thing I wanted to do was I just did a straight assign using the assignment operator, and with a vector we can use the same array index syntax that an array does. So myvec sub 3 is now going to assign 95, 95 to myvec sub 3. So we can, it sort of looks like an array when you use that, the brackets as our subscript operator. And we can treat it like an array, in this little aspect. You can do a direct assignment, and it's going to just assign whatever we got there. So there's my a couple of extra values that I wanted to assign here, just to show that okay, these made it into the vector, and I'm hoping to get rid of them now. So here's that first output, this line. And you can see it's got the 95, 95 and the 84, 84 in there. All right, so now to delete that range then, we're gonna use the dot erase method again, just like before, except we just have to declare the starting one and the ending one. And just remember that ending one is non-inclusive. So if we want to delete 3, 4, 5, and 6, then our ranges have to be 3 and 7. Because we start deleting it at 6 and we stop right before we get to 7. So this will be no different. So there's the two offsets we provide. myvec begin plus 3 is where we start, and myvec begin plus 5 is where we end. And then over here in our run of the program, we see that, yep, those two elements came out, and now we're just left with that round of 200s in there. Okay, Benji had a question. Is it just as straightforward to delete every element equals 200? So I guess, is your question, is it easy if the element happens to be 200 to delete it? Yeah, absolutely. Just simply delete it. And in this case, it might end up with an empty vector because all of the elements were 200. But yeah, code like that would look just very simple. We would go through it. Come on. I want a reminder that a vector can report its size at any time with the dot size method. And then here, what we would do is, as we go through this vector, we would just say, if If my vec sub I equals 200, well, then we would just simply delete that one. And we know what the offset is there. So. All right. And that's it for a very quick primer on vectors. Hopefully very quick. Questions? So I'll awkwardly pause for about 5 more seconds with this kind of an expression on my face. Questions? All right, I think we're good then. I'll stop this share. And then just as a reminder, that code is already posted to Canvas. So you can pull it and run it and play with it to kind of get your mind around these vectors again. And again, we'll be using a lot of vectors in this course. So make sure that you've got a real good handle on just how to manipulate those. All right, oh, let's see, there's one more question here. Oh, we got a thanks. All right, good. Okay, so that's it for today, gang. I will see you all next on Wednesday afternoon, and we'll do a review of structs. And that's gonna kind of get us set up for our very first data structure, which will be, yeah, I hope to get to it next week. We've got it, we miss a day of class Monday, but I hope we can get to it on Wednesday. We'll do a quick pointer review and then get to our first linked list. All right, gang, that's about it. Message me if you've got any problems, and I'll talk to you later. All right, thanks for joining.